Hello all. So today we will talk about exercise 8.53, swirling around the cone. So this question is about, here's a cone, and there's a small platform at this point, at the midpoint of the slope, and there's a small sphere that's rolling, a particle that's released from rest on the inside surface. And keep in mind that this platform is positioned to be 45 degrees. So just try to imagine if this was one of the sides of this cone. So just imagine if I open up this cone, then the platform will look something like this. So it is aimed at 45 degrees Celsius, 45 degrees. And so that is what the question means when it says the platform is positioned at a 45-degree angle along the surface of the cone. So when the ball falls down, it will be given, the velocity will be converted into both a horizontal component and a vertical component. So that's something to keep in mind of. So let's think how we can do this problem. So first, you might be tempted to use kinematics, but kinematics doesn't really apply here because what we've learned is, the formula is like v naught t plus half gt squared equals to h. Like these kind of formula, they are only for flat surfaces. But in this scenario, the cone is a curved surface, and so the acceleration is really complicated. So especially with, there's also normal force. And so we can't really use kinematics here. Like these formulas just wouldn't apply. So let's try to think of another way. Let's write out what we know first. So how I think about these problems, that I first try to write down what I already know. So obviously we need to set up some variables. So let's call this point, this distance d1. So d1 would be the distance from the sphere to the platform, and d2 would be the distance from the platform to the bottom. And we know that d1 equals to d2 since the question said that the platform is at the midpoint of this surface. And so let's just call it d. So not d1 and d2, so they are all d. And then obviously here energy is conserved because there is no friction. And so obviously we can get an expression for the velocity of the sphere when it falls down to the platform. So what would that be? That would be, so if we call this angle theta, so like the angle between the slope of this cone and the horizontal ground would be theta. And so we know that this height right here, it would be d sine theta. And so from the conservation of energy, we know that mg d sine theta equals to half mv squared. Let's call that v naught squared. So v naught represents the initial velocity when the ball falls down to the platform before any collision. And so what would v naught be? Well, we can cancel out m, so we get v naught squared equals to 2gd sine theta. And so we know that v naught equals to square root 2gd sine theta. Okay, that is very useful. So the question is asking us to find the ratio of the particle's maximum swirling height to the height of the platform. So it's basically asking us, like, when this sphere comes down and hits the platform, when it bounces up, or rather when it swirls around, the maximum height, that ratio to the ratio of the height of the platform, which is d. We're trying to verify that the ratio is square root 5 plus 1 over 2. So what are some other things that we can use to solve this problem? Well, we can think about force, but force inevitably leads to calculations about acceleration, which again complicates things because kinematics is involved and we don't want that. So what about conservation of angular momentum? Since we already used the conservation of energy here, what if we can find a conservation of momentum to find v naught or some other velocity, and then we can relate these formulas to get a ratio for this question. And so let's consider the angular momentum around this axis. around this vertical axis which bisects this cone. We know that the torque around this axis is called let's call it the z-axis. So we know the torque around z is conserved. Why? Well, because we know that no force contributes torque around the z-axis. So if we have a sphere here, we have gravity and we have normal force. Now, this is the z-axis, and this would be the distance of the sphere to the z-axis. Now the normal force, the horizontal part, points towards along this axis, so it provides no torque. And the y component of this normal force doesn't contribute any torque either, because it points along the z-axis. And the same applies to gravity, which points straight down along the z-axis. And so we know that torque around z is 0. And so we know that the angular momentum around the z-axis is conserved. So how can we use that? Well, we know that when this ball bounces to the highest part, it is traveling in a horizontal circle sort of way, or only for an instant. And so maybe we can use the angular momentum of that point and equate it to the angular momentum of the sphere when it first bounces off this platform. Since we already have v0, let's try to find what it was before, like initially when it first bounces off the platform. So the formula is mvr. So what is r here? R here would just be d sine theta, because remember, the sphere is right here at this point when it first bounces off the platform. And so we have mv0 times d sine theta, d cosine theta. And keep in mind that theta is just this angle. And so d cosine theta would be this distance, which is the radius. And then what about when it bounces off? Let's call it L final. So when it is at its highest point of some sort, let's say here, or no, let's say it's here, when it bounces up during when it is swirling around the cone. Let's call the angular momentum at this point LF, although it's equal to L0. And so what would LF be? LF would be m times v final. So let's call the velocity of this sphere at this point v final times r final. And so now we just need to try to find RF to relate these two formulas, and then we can get VF and V0, and then we can connect it to these formulas, to the conservation of energy, and then we can later find the answer. So how can we do that? Well, we know that at this point, let's call this point H. So let's call this whole height, the maximum height, capital H. So we know that the RF is just H cosine theta. And then we need VF. And what would VF be? So if we again utilize conservation of energy, we can write out half mv0 squared plus mgd sine theta equals to half mv final squared plus mgh sine theta. And so then we can get VF in terms of these variables. So let's sub in this equation to this formula. So we have half m times 2g d sine theta plus mg d sine theta equals to half mvf squared plus mgh sine theta. And then later we can also substitute this formula. Since we know that L0 is always equal to LF because of the conservation of energy, of angular momentum, we know that V0 d cosine theta is always equal to V final h cosine theta. So cancel out the cosine theta. We know that VF equals to V0 times d over h. And so then we can sub in and write half m v0 squared d squared over h squared plus mgh sine theta. And then this side we have, we can simplify a bit. We get mgd sine theta. And this is also mg sine theta, so I'll just write 2. And again, we can sub in the v naught of this formula to here. And so 2 mgd sine theta equals to half m 2gd sine theta d squared over h squared equals to mgh sine theta. We cancel out the sine theta. And then we can also cancel out the mg. And then here you can cancel out the 2. We have 2d equals to d cubed over h squared plus h. And so now, remember, the question is asking us to find h over d, this ratio. Remember that h represents the maximum height, and d is just the platform height. Or rather, to put it more precisely, it's h sine theta and d sine theta we're finding. But we can cancel out the sine theta already, so just h over d that we're trying to find. So how can we do that? Well, there's a quicker method instead of rearranging this formula. Let's just set the answer we want to find as x, which is equals to h sine theta over d sine theta, which is equals to h over d. And so why don't we divide this formula by d? So you get 2 equals to d squared over h squared plus h over d. And so then it will be 2 equals to 1 over x squared plus x. And then we can multiply x squared, so we get 2x squared equals to 1 plus x cubed. And we can solve this formula, so we have x cubed plus 2x minus 2x squared plus 1 equals to 0. And if we solve them, we get 3 roots. We get 1 would be negative 0.618. The other one is 1, and the last one is 1.618. And the question asks us to verify that it is square root 5 plus 1 over 2. So we're just trying to find the root that corresponds to square root 5 plus 1 over 2. And if we pull out our calculator, we find that 1 plus square root 5 over 2 equals 1.618 exactly. And so that in that way we verified the proposed value, and that is our answer to this exercise. Thank you for watching.